Hello everyone, welcome back. In this video, we'll be discussing about the last problem of yesterday's biweekly contest, find products of elements of big array. The problem is a bit difficult just because it requires you to make certain observations and build formula based on that. So in this video, we'll be going through all the different observations involved and solving it step by step. Having said that, because this involves mathematics, I would assume that you know a little bit of bit manipulation, not much is required. And even if you don't know, I think you will be able to understand the solution or the core behind the solution itself. So with that, let's get started. The problem states that a powerful array for integer x is the shortest sorted array of powers of 2 that sums up to x. For example, powerful array for 11 is 1, 2, 8. This is simply a nice way of saying that represent a number in its binary format. So when you represent number in its binary format, you will get sum of powers of 2, and that is the shortest possible sorted powers of 2. So if you represent 11 in binary format, you will get 1, 2 and 8, right? So basically a powerful array of x is simply the binary representation of x. Now the array big nums is created by concatenating the powerful arrays for every positive integer I in ascending order. So you will create powerful array for 1, powerful array for 2, 3 and so on and so forth, and create this big nums array. So first you will have 1, then you will have 2, 3 is represented as 1 plus 2, so it is 1 and 2, 4 is represented as 4, 5 is represented as 1 plus 4, so 1 and 4, 6 is represented as 2 plus 4, so 2 and 4, and 7 is represented as 1 plus 2 plus 4, so 1, 2 and 4, and then 8 is represented as 8 and so on and so forth. Now you are given certain queries. Each query is of type from I to I and mod I, and for these query you need to calculate big nums all the way starting from up to 2 modulus mod, right? And you return the answer for each of the queries that you have been given. So that's the problem. So let's take one small example. Let's say queries is 137. That is, you need to take big nums of 1 multiplied by big nums of 2 multiplied by big nums of 3 modulus 7. So if you see, big nums of 1 is 2, big nums of 2 is 1, and big nums of 3 is 2. So 2 cross 1 cross 2, which is 4. 4 modulus 7 is 4, and hence answer here is 4. Okay, so hope the problem statement at least is clear. Now we already made one simple observation about powerful array. That powerful array is actually a nicer way of saying that you need to represent the array in binary format. Now we need to figure out the product of some integers modulus module, right? And each of these expression is actually one of the values from this big nums array, and each of the value of big nums array is coming from one of the powerful array. This in turn means that each value here will be a power of 2. Just rewind the section if you don't understand this, but overall this everything here is a power of 2, right? So what we are saying is we have to multiply certain power of 2's and do a modulus mod, right? So this is what we have been saying. So big nums of from of I would be some 2 power x1, big nums of from of I plus 1 is 2 power x2, and so on and so forth up till let's say 2 power xi. And if you multiply them by simple mathematics, it will be 2 power x1 plus x2 all the way up to xi, right? Modulus mod. Now you can compute this easily, even though this entire thing is very huge, by using fast exponentiation and like you can do that with first estimation easily, but let's first figure out what is this value. Now, one way to figure out this value could be, okay, I will find out everything from +1 all the way up to 2 and sum it up, but that is surely not possible because the values of these indexes are actually very huge and you can't enumerate this big nums array, and that's where the complexity lies, right? So you can't enumerate x1, x2 and x all the way up to xi, and hence you can't get this sum easily or by iterating over all these xi's. So one of the approach would be, okay, let me figure out the sum of powers of 2 up till this index, and let me figure out sum of powers of 2 up till index from -1. I will subtract these two and I will get sum of powers of 2 up till this particular up till the index in between from and to, right? So that's the very standard way in which of computing sums. Like if you want to compute a range sum, you will simply do a prefix sum for everything up till r and prefix sum for everything up till l-1 and subtract these two to get everything between l and r, right? So that's like the standard technique. We now got count, like this is the function we now need to implement, count of 2's till index, and given an index, tell me what is the count of 2's up till this index. And if you are able to implement this function efficiently, we are good to answer this query, right? So the rest of the video we will be focusing on count of 2's till index. So let's enumerate our big nums example again, and as we discussed, this is 1, this is 2, this is 3, 4, 5 and so on and so forth. Now let's assume that the value of index is 10. That is, we want the count of 2's, or rather sum of powers of 2 up till index 10. So in this particular example, what is the answer? Answer would be, there is 0, 2 here, there is 1, 2, 0, 2, 1, 2. So basically we got 2 2's, then there is 2 2's here, so 4 2's, then 0, again 2, so total 6 2's we have, 1 which is 7 2's now, 2 more 2's which is 9, 0 and then 1 more 2 which is 10. So overall we got 10 2's. So basically count of 2's till index 10 will be equals to 10, right? So this is what you need to answer. So would encourage you to at least pause and try to think a bit around how to solve this. So notice one thing. Let's say you have built a formula. Now whatever formula you will build, you will be able to build that formula for a integer. That is, you will say, okay, I want to know what is the count of 2 until x, right? And x, like you will just iterate from all the power array up to x. So in this case, x would be 6. You will say, okay, I will compute all the powers of 2 up till 6 separately, and whatever is left, I will compute that separately, because the leftover is basically something which doesn't fit in one full integer. So 7 is considered as 1 plus 2 plus 4, but you want up till 10, so not the entire 7 is captured here. So what we are saying is, we will figure out some formula for calculating everything up till integer, and whatever is left over after an integer, we will calculate them manually by going over them one by one. Now, is this efficient enough? The answer is yes. Why? Again, go back to the first 5-10 seconds of the video where we were discussing about this powerful array definition. So we were saying that it is the shortest array of sum of power of 2, right? So if you have to represent an integer in its binary format, you will always get at max log n number of powers if in the shortest array, right? So whatever integer it is, you will just get log of that integer, let's say n, number of these different powers, right? And in this case n is 10 power 15, so you will get at max log of 10 power 15, which is less than 64. So it is actually feasible to get some formula up till an integer, or if not formula, some pattern to figure out the count of 2's up till an integer, and whatever is left over for the next integer I will calculate that manually. So that's the trick. We will simply this is our overall pseudo code that we will be trying to execute. First we'll figure out what is the nearest integer, right? So we are at index 10, right? We have to first figure out what is the nearest integer that is before or up till index 10 which is full. So in this case this will come as 6, right? So we need to first figure out this, right? Let's say there is some function, we'll worry out later how to implement this function efficiently and so on, but there is some function for that. Now then we are saying that okay, I will figure out a way to find the total sum of powers of 2 up till that integer, right? So every powerful array up till that integer we will consider and figure out the sum of powers of 2. Now the next integer is not full, so we will simply iterate over the entries of the next integer and include their powers of 2 manually. So this is our next integer. We will iterate over the binary representation of this number manually. Now how many expressions to include here? Like we have 3 expressions for 7, so how many of these integers to include? That will depend on how many we have exhausted up till the last integer. So in this case we also need some function that will tell us okay, how many terms are there up till a particular index, up till a particular number x, right? And if you minus that you will get what is less. So in this case if you pass 6 you should get 8, and you will simply say I need 2 more integers from whatever 7 will decompose into. So I will then simply iterate over all the binary representation of 2. Again, this is a very simple trick to iterate over the binary powers of 2. Basically we are simply iterating from the front. Why front? Because the powerful array will be a sorted array, so we will be iterating from the shortest to the largest. So we'll iterate from 0. This is a simple way to check whether this bit is set or not in the binary representation. So if it is not set, we'll continue. If it is set, we'll check if we really need to take any number. If we don't, we'll simply break. But if we need to take a number, we'll simply decrement the required number of numbers to take and increment our answer by I. Why I? Because I denotes what is the power of 2. So basically here I denotes 2 power I will be there in the current position, and because it is 2 power I want this sum of powers of 2, so I will be contributed to the sum of powers of 2, and hence I will simply add I, right? So that's the overall algorithm. Now this algorithm depends on 3 different functions: next nearest integer, count of 2 till x, and terms till x, right? If you are able to implement these 3 functions efficiently, rest of them we already took care of. This entire thing is simply order 60, which is fine. So let's first focus on count of 2 till x, and then we'll focus on the other 2 as well. So what we need now is count of all the 2's up till integer x. So for example, if x is 4, what I want is, if you represent everything from 1 to 4, let's say 1, 2, 3 and 4 in the binary powerful format, which is 1 is represented as 1, 2 is represented as 2, 3 is represented as 1 plus 2, and 4 is represented as 4, then how many powers of 2 are there? So in this case, this has a power 1, this has power 1, this has power 2, and rest has power 0. So overall 4. So up till 4 we got sum of power of 2 will be 4. So that's what you need to answer. And if you are able to answer this, like you have to answer this efficiently. You can't iterate from everything from 1 to x, because x in this case can be very huge, right? So that brute force way would not work. So how to approach this? So whenever these binary things are involved, try to work out a solution for a power of 2 itself. So for example, let's say we'll assume that x is a full power of 2. When x is not a power of 2, how to solve that, we'll come to that. But for now, what we are assuming that x is a power of 2. For example, x is 2, 4, 8 or so on and so forth. So in this example, let's assume that x is 8, right? Or rather x is 16, right? In other words, we want everything up till 15 or 16 integers, like starting from 0 to 15, right? Now you want the sum of powers of 2 for all these numbers. How to do that? So what we have to do, we have to count these ones. Let's say this ones occurs some x1 number of times. Here number of ones occur x2 number of times. Here number of ones are x3 number of times. And in the fourth one, number of ones is x4. Now in this scenario, what is your answer? Your answer would simply be x1 multiplied by 3. Why? Because this is 2 power 3. This is 2 power 2, this is 2 power 1, and this is 2 power 0. So x1 multiplied by 3, 3x1 plus 2x2 and x3. This will be your final answer, right? Now if you can figure out x1, x2 and x3 efficiently, your job is done, right? Now what we need to figure out is how many ones are there in each of these columns. Now here comes the very first and the most important observation of this problem. Whenever you have a binary, whenever you represent the binary numbers, or rather whenever you represent numbers in a binary format, everything will be a mirror image of each other. So in this case, let's start with a 1-bit number only. So let's focus on these 2 bits for now, right? So if you focus on these 2 bits, these 2 bits are mirror images of each other. So 0 is mirrored to 1, right? So if they are mirror image of each other, number of 0 and number of 1 would be equal in 1 bit, right? Now let's go to 2 bits. If you go to 2 bits, again they are mirror images of each other. So this 0 0 will become 1 1, this 1 will become 0, or rather this 0 1 will reoccur here, which is 0 1, right? So again, number of zeros, whatever was here, will be there in the second half as well. And because number of 0 and number of 1s are equal here, number of 0 and number of 1s will be equal here as well, which in turn means number of 0 and number of 1 is equal here in this entire column as well. And what will be the count? The count will come to that in a bit. So for now, what we notice is number of zeros is equal to number of ones in each of the column. I'm not talking about the first column because first column is very self-evident, like you had all zeros previously, now you had exactly same number of integers, so and that has all ones, so number of 0 is actually equal to number of 1, right? So in both the columns, number of 0 is equal to number of 1, that we know. Now let's go to 3 bits. So all of these were 0 previously and all of these are 1. So on the first column, everything like number of 0 is equal to number of 1. Now is it true for the second column? Answer is yes. Why? Because again this entire thing will be repeated, 0 0 1 1 0 0 1 1, and because number of 0 and number of 1 is equal here, number of 0 and number of 1 will be equal here as well, which in turn mean number of 0 and number of 1 is equal in this entire column as well, and same argument applies for the third column as well. So we see that number of 0 and number of 1s is equal in each of this column, and if you expand this to fourth one as well, all of these were 0, all of these will become 1, exact same argument. Number of 0 and number of 1 is equal in first column, For the second column, this is a complete repetition, right? And because it is complete repetition, number of zeros and number of ones, whatever was there here, that will be the same count here. And because number of zero and number of ones are equal here, number of zero and number of one will be equal here as well, which in turn means number of zero and number of one is equal in the entire column as well. And similarly, second and third and the fourth column as well. So with this exercise, we at least know that number of zeros and number of ones are equal in each of these columns. But we actually needed count. We want the value of x1, x2 and x3. So what is the total number of zeros or total number of ones? If we are able to find any of these, we are able to find our answer. So for that as well, just try to pause and think for a moment. I think you will be able to make the observation yourself after this exercise. So I hope you thought about it. It's actually equal to half the number of numbers. Why? Let's talk about the first bit itself. So in the first bit, number of zeros and number of ones were equal, and there were two numbers. So overall, there is 1 0 and 1 1, right? Let's talk about second bit. So in this case, you have this half. Number of zeros and number of ones are equal in the first column, and because everything was 0 above and everything is 1 below, it is clear that number of zeros and number of ones is equals to half the total number. There are 4 numbers, so number of 0 and number of 1 is equals to 2, right? But what about this column? Here we know that number of 0 and number of ones are equal, but what's the count? So for that, think about what's the count previously. Previously the count was 2, or rather what's the previously the count was whatever was the count divided by 2, right? So previously the count was 2 power 1 divided by 2. That was the count for number of zeros and number of ones, and we know that exactly the same count will be occurring here. So this will simply multiply by 2, which in turn means number of count is equals to 2 power 1, which is equals to the first column, right? And if you expand this argument further, you will realize that actually every column has equal number of zeros and equal number of ones, and further they have exactly half zeros and half ones. Okay, and because of this observation, we can say that x1 will be equals to x2 will be equals to x3, and they all will be equals to some x. So what we are saying is all will be equals to some x. X multiplied by 3 plus 2 plus 1 will be our answer. And what is the value of x? The value of x is simply the total numbers by 2. So in this case, total numbers were 16. So the value of x would be 16 by 2, which is 8. So this is our total sum of powers of 2 all the way up to 16, or all the way to 16 numbers. Not 16, it is up to 15, 0 to 15, but 16 numbers, right? Now, can we generalize this? Answer is yes. 2 power 4 is 16. So 2 power 4 by 2 multiplied by this thing. So if you look at this generally, this would be 2 power whatever is the largest power here, or rather let's say if you are talking about 16, power is 4, right? Similarly, if you talk about 32, power is 5, and so on and so forth. So whatever the largest power that comes here, divide by 2 multiplied by the largest power plus largest power minus 1 plus largest power minus 2 all the way up to 0, right? So this entire thing is simply a simple arithmetic progression, which is n into n plus 1 by 2, and this entire thing is simply 2 power largest power, let's call it L, let's call largest power as L. So this is simply 2 power L by 2, which in turn is 2 power L minus 1. So if you expand this entire thing, this is how it will look like: 2 power L minus 1 multiplied by L minus 1, L minus 2, L minus 3 all the way up to 0, right? And if you sum this AP up, you will get L into L plus 1 by 2. That's the usual formula, but here L is L minus 1, so you will get L into L minus 1 by 2. So because you had 2 here, you can take this as negative power, one more negative power, so this entire thing would become L minus 2. So this is the formula for sum of powers of 2 up till sum x, which is actually a power of 2, right? Now this works for 2, 4, 8, 16, all the way up to any power of 2, but we need a generic version of this because x can be anything. It can be a number which is not a power of 2 as well. So how to tackle that? I would strongly encourage you to pause and try to think about it yourself. So what we need is, let's say we want to figure out the value when x is equals to 13, count of powers of 2 up till 13, right? So hope you thought about it. The solution is actually built from the previous solution itself. So we know that we can compute the values for any powers of 2. So in this case, the nearest powers of 2, which is full, is 2 power 3, right? So we know that we can compute this value here. So in other words, we know what is the total sum of powers of 2 for all of these, right? What we don't know is what is the total sum of power of 2 for all of these, right? But we know one thing for sure, that everything in the first bit will be 1 here. Why? Because you are covering everything after the next after the previous highest power. So in that everything would have been 0. Now after that everything would start with 1, right? So you know one thing for sure, that everything is 1 here. What that mean is, if it is 13, how many integers you have? 13 minus 8 plus 1, which is 6. So you have 6 integers here, and all of 6 will have this as 1. In other words, all of these 6 will have 2 power 4, right? So in other sense, you have like 6 into L as your sum already. Now you have taken care of all of these as well. So what you need to take care of now is this entire thing. And remember, this entire thing is just a copy of the above. So which in turn means this is 0, this is 1, this is 2, this is 3, this is 4, this is 5. So which basically translates to, give me all the sum of power of 2 up till 5. Isn't this exactly the same problem as the original one? Because original one had, give me everything, give me the sum of powers of 2 up till x. So initially we called it with 13. Now after figuring out the values all the way up to 8 and also removing or computing the values for the remaining ones for the first bit, we are saying that we want a count of 2's till x, where x now is 5. And we can do the exact same thing for 5 as well. Let's say this is 5 here. We can say what is the nearest power of 2. So we can compute everything up till the nearest power of 2, that we know the formula. We can do it in just order one time. After that, we also know how many are remaining. So for those two, you already know what is the contribution of the first bit. Now what you need to know is this particular thing, and this is again simply 0 and 1. So you will just call the same function with 1, and 1 could be your base case or 0 could be your base case, whatever you want, and hence it would end, right? So what you're doing is, at every iteration you are removing or cutting down one complete bit. So overall it will take log n iterations to complete this entire process, and you will get the final value, right? So what is the overall algorithm is, figure out the nearest power of 2 with the formula, figure out the nearest power of 2 and then figure out the sum of count of 2's with the formula for this nearest power. Now everything afterwards will start with 1 for sure. So just remove those contribution by counting the number of elements afterwards, and that you can do simply by doing subtraction of this with the nearest power of 2. Once you get that, whatever you are remaining with will simply be 13 minus 8 because the first bit is completely gone, everything is afterwards. So you can simply remove the first bit here, which is 13 minus 8, which is 5. So you can simply compute the values for 5, and in the same fashion for 5 as well, you will do the exact same thing. So the pseudocode for this would be something like this. What you're doing, you have some base case. Now what is your base case, I will leave that to you. You can treat it in different fashions, but the core algorithm is you will figure out the nearest power of 2. This you can do easily in just order log n time, or order n time as well. There are different tricks to that as well. After that, you will apply the formula for this nearest power of 2 that we derived previously, and then you will figure out what are the remaining elements. These are the remaining elements. For all of them, the first bit will be set, and the first bit will contribute 2 power L, or rather L. So you will simply add everything multiplied by L, and afterwards you are left with these all indexes or these all integers. You will simply call the same function for these all integers, and this entire iteration will take log n time to finish, and you will get the final answer, right? So just to recap, we started our journey with this particular algorithm. We said that we need 3 different functions: nearest integer for index, count of 2 till x, and term till x. So for count of 2 till x, we have implemented this in order log square n time. Again, this can be done in log n as well, but for now let's assume that it is log square n. So we have implemented this entire thing in log square n time. That is okay, like we can afford that. Now is the time to compute these 2 things. So let's focus on terms till x for now, right? And just to reiterate, what was terms till x? Terms till x was simply how many terms are there up till x. So in this case, if x is 6, number of terms till x will be 9. Like there are 9 terms until x, right? So that's what we need to figure out. So again, if you want to, the approach is exactly what we have just discussed. So this is the very good time to pause and try to approach this part by yourself. Okay, so let's start. We want to figure out how many terms are there. In other words, we want to figure out how many ones are there. Like each of these one will be a one term in the array. So if I talk about 1, this will be one term. If I talk about 2, 2 will have one term. If I talk about 3, 3 will have 2 terms, 1 and 2. Similarly, 4 will have just one term, 5 will have 2 terms, and so on and so forth, right? So we just simply need to count the number of ones here, right? So this is even easier than the previous one, because we already know that number of zeros and number of ones are equal, and they are equals to the total numbers by 2, right? So we can utilize that fact again. So the process will be exactly same. We will first figure out the value for a power of 2. So we'll first assume that x is a power of 2, that is 2, 4, 8, 16, or so on and so forth. So for now, let's assume that x is 16. That is, we want everything up till 16 terms, or rather up till 0 to 15, we want the count of terms so far, right? So again, count of terms would simply be number of x, number of ones here, which is, let's say, x, number of ones here, number of ones here, and number of ones here, right? And each of these will contribute one term in there. So overall you have like 4x number of terms, and this x, what is the value? The value is simply 2 power, or whatever is the largest power. Let's assume that it is L. So 2 power L by 2, 2 power L is this particular, 2 power L by 2 is the value of x, right? Count of ones. And this 4 is also not exactly 4, it is like number of powers or number of bits that we are considering, right? So overall this is how it will look like. You have 2 power L minus 1, which is this particular fact, which is the count of ones, and then 1 plus 1 plus 1 all the way up to L times, and you will simply have 2 power L minus 1 multiplied by L. So this is the formula for x being a power of 2. Now x may not be a power of 2. Again, let's take with the same example 13. if you want to figure out number of terms until 13, how will you do that? You can again utilize the same trick. You can say, okay, I know everything up till 8, I can figure out with a formula, and I don't need to worry about this bit because all of them are 0. So up till 8 you can apply this formula and figure it out. Now after 8, everything is 1 here for sure, right? So all this contribution I can take. So number of ones is 13 minus 8 plus 1, which is 6. So now I can just simply add 6 to my answer, and for rest of them I can call the exact same function because it is simply terms until 5. You can call the exact same function and you will get the answer, right? So exact same algorithm, and it will also work in order log square n time, right? I'm not showing you the pseudo code for this because I want you to code this by yourself. So for now, what we have done is we have solved term till x in log square n as well, and this is already log square n. Now what is remaining is nearest integer. Now just to recap, what is nearest integer? Nearest integer is if I give you an index, let's say 10, in the big nums array, you need to let me know what is the nearest integer which has all the expressions or all the values of their power array included up till that index. So in this case, for 10, the answer would be 6. So that's what you need to figure out. So this is the last part, and honestly, this is also exactly the same approach. We just need to simply, like, let's say you want what is the nearest integer up till here, right? So you already know how to compute terms, right? So what you can do is one of the algorithm could be just iterate over the integers and call this terms till x, right? And if it is less than equals to index, you will simply continue, and if it is not, the first time it is greater, just return the previous value because that's what is the term which is completely included, right? So if you want, let's say 10, you will get for 6 you will get 8, and for 7 you will get 11. So at 11 you will break out by returning 6. So that's the algorithm. Now this algorithm is not optimal. Why? Because you are iterating over every terms, and number of terms you are iterating over every integers, and number of integers could be very huge. It depends on the value of the position as well. We have seen that it is like L multiplied by number of numbers by 2 overall, right? So this is like not that huge. So this iteration can go all the way up to index as well in worst case, right? So this will be of the order of index, and index is 10 power 15. So we can't afford this at all. We need to optimize this. Now how to optimize this? We are doing a linear search here. Let's see if we can apply binary search. If we can apply binary search, this entire thing will simply be log of n, and that should be fine. So in this problem, we can indeed apply binary search. Why? Because this is a step function. Like it will be decreased, it will be lower up till index, and at index it will be upper, and then will stay upper. And we just need to find out this deflection point. And how to figure out that? Let's say we have a sample space. You will simply do a binary search, that is divide this sample space into half, figure out what's the total number of terms up till this integer x, right? And if total number of terms is greater than this index, then you know that what you're looking for is in the left. So you can completely skip the right half and search in the left half. But if number of terms is less than index or equals to less than index, then you will simply search in the right half. You can skip in the left half, right? So that's how you can simply apply binary search and convert this entire thing to just log of index, and that is also efficient, right? So what you're doing is you are doing 3 log square kind of operations, and everything complexity wise it will be log square n, and you have total 500 queries. So 500 multiplied by log square n, which is very small, right? So this is the algorithm. I would strongly encourage you to pause and try to code this entire thing by yourself, because this still includes plus minus 1 somewhere, which I have intentionally skipped. So if you code this entire thing by yourself, you will yourself understand the nitty-gritty details to this implementation. Again, I would reiterate that this problem was not like implementation heavy, because a little bit plus minus one you will be off. So during the contest I was not able to fully code it. After the because I was missing plus minus one somewhere, I didn't recall where, but I was missing plus minus one somewhere. So after the contest I tried after 1 hour, and it was simple mistake, and that got accepted. So let's look at the code. Again, before proceeding, I will strongly encourage you to code this entire thing. This code, I have literally coded the functions that we have just discussed, right? So we will answer for all the queries. For all the queries, we will first figure out count of 2 until index I, like 2 and then from. Now my index is 1 based indexing, so that's why I just do +1 here, and this from -1 is simply from. Now after that, this count of 2 till index, we have done exact same thing. This is the base case, and we have done a binary search to find out which index is the nearest one which has all its powerful expressions in, right? So we simply figure out the terms till m. If it is greater than or equals to index, we'll go and search in the left half. If it is less than, we'll go and search in the right half. So that's the binary search part of it, which is discussed in the last part of the video, right? Nearest integer index. After that, we will apply what algorithm we have discussed. We will first take count of everything up till this index or this integer, then figure out how many terms are remaining, and for each for the next integer I will simply, this is the next integer, so for next integer I will go over the terms one by one and include that if it is required, right? Now let's figure out these two functions, count of 2 till x and terms till x. So let's first go to count of 2 till x. This is like the base cases. Again, there can be a bit less base case as well, but that's what I ended up coding. This is figuring out the largest I, which is simply 2 power L, like the value of L here, and then this is the formula for the answer, and then after that whatever is remaining I will multiply with L, because this is what we wanted to take. For the remaining ones, we know that everything will start with 1. So for the remaining ones, I just simply this is the remaining ones. So for the remaining ones, I simply added largest of I contribution for each of them, and for the rest of them I will simply call the same function with the value. Now terms till x is exactly a carbon copy. We figure out the value largest index or nearest power. After that we simply did 2 power L minus 1, right? And then we figure out the remaining ones. For each of the remaining ones I will add 1, so this is the remaining one, and for the remaining ones I will also need to go and figure out their sum as well, so we'll just call the same function. So that's it. If you have any doubts, feel free to post them in the comment section below. I would be happy to answer. Okay, one more thing before I forget. So you need to do this 2 power I. So that for that you need this fast power, which is like standard implementation of fast power, right? So that's pretty much it. If you have any doubts, feel free to post them in the comment section below. And if you think you learned something from the video, do share it with your friends so that they can also get benefited. With that, we'll end here, and I will see you next week. Thank you.